Okay. All right. Well, good evening, everyone, and welcome to the 2022 series of reliability webinars. My name is Paul Phelan. I'm a member of the Media Asset Management Society of Engineers Ireland. This is our second webinar of 2022. So thank you all for attending. Format for tonight, we're going to do about a 45-minute presentation. And then there's going to be 15 minutes for Q&A at the end. So if you'd like to ask a question, if you could please put it into the Q&A box at the bottom of the screen, and I'll get to them in turn at the end. So I'd like to introduce tonight's speaker, Stuart Walker from RMS Reliability. He is condition monitoring. He's been working in the condition monitoring and reliability sector for the last 25 years. He started working for DuPont as a mechanical and production technician, and after completing a 4-year apprenticeship. So it was here he's introduced to condition-based maintenance, and he set up a successful program at one of DuPont's UK sites. And he also used vibration analysis, oil analysis, infrared thermography, and he moved the site from time-based maintenance strategy to a predictive and proactive one. So that's something that everybody's really doing at the moment, you know, but Stuart's been doing it for the last 25 years. So there you go, he's got a head start on everybody. Okay. In 1999, he set up Reliability Maintenance Solutions with the famous Dean Whittle, and together they have successfully grown the company over the last 22 years. So RMS provides reliability consultancy, training, service, and products to a number of blue chip companies across the UK, Europe, and Middle East. And Stuart has worked in many industry sectors, including oil and gas, petrochemical, power, and paper. He is currently working on projects introducing and implementing the new motion amplification technology within RMS and across a wide range of industries at home and abroad. So this is something that is, I guess you could say, particularly close to my heart. I've been using this for the past 5 years, but it was RMS that introduced me to the technology 5 years ago. Prior to that, I'd only seen a little video of it up on LinkedIn, didn't really know what it was. But since I've started using it, I think it's been great. I think it's been a game changer, and it's been used on stuff that I, beforehand would never have even thought about using it, or wouldn't even know how to use it. So I've used it on problems. I've used it on structural support problems, as well as the foundations for motors, gearboxes, pumps, you name it. There's also small bore instrumentation we've used it for. I think it's great. What I've said before is that, give me a 2-channel analyzer and give me a motion amplification camera, and I could probably solve anything, which is a statement I might live to regret at some stage. But it's if you have the two things, I think there's pretty much not much that you can't solve. That's one thing I would say. So I think I've said enough. I'm going to hand over to Stuart Walker and enjoy the presentation.
Yeah, thank you very much, Paul. Thanks for the introduction. Yeah, it's really interesting, this technology, and I hope this presentation you get something out of it. I'm going to start off by covering some of the background about the technology, and then we're going to look at some real world case studies, which hopefully you'll get something out of. So just before I start, what amazed me with the technology, that initially when I first came across it, I was very skeptical, actually. When something looks too good, you do question it, and that was definitely the case for me. But once I'd had a couple of demos done on some resonance problems, I was blown away, and ever since there we've incorporated it with the other technologies we use, and like Paul says, it really is a bit of a game changer. So let's get cracked on. So cameras everywhere now. We used to having cameras in society. They're used to discover new galaxies. We've got controlling traffic, these Google, all this stuff, sending me bills. It's phenomenal now, the use of cameras. And now we can obviously use it for vibration and machine monitoring. So what is motion amplification? Well, really, in its simple terms, I'm going to play this video, is we can actually see vibration now. So we can amplify the motion, the vibration, the individual frequencies And when we do that, we can actually start to see how the machine moves, and this can give clues to problems. Here we've got a motor and pump, and you can clearly see the base has got an issue. There's some movement there, and we can even do non-contact measurements. So let's look at another example. So again, this is what we see with his eye, and then we've filtered to the pump speed, which I think on this one's 3000 RPM. And you can see we've got serious movement on the floor there. That's what you see with your eye. And then with motion amplify, you can actually see a crack there in the concrete. So it is really very visual technology. And in this case, you can see there's a new piece of steel pipework there. That had a previous failure. They've put a new piece in, but because they haven't addressed the root cause, that pipe's going to most likely fail again. So it's very powerful communication tool. We can also do non-contact measurements with this technology. We do need the distance to achieve that. So we use a laser to get the distances for that, but it's as accurate as you would normal accelerometer. And because it's non-contact, here we did a bit of work with one of the Formula One teams. We've got a car there on a rolling road. There's obviously glass in front, and we can do non-contact measurements. So it truly is quite remarkable technology. Further developments being done on looking at transient, so we can actually lock onto a component that's moving and actually track and measure the vibration over time. So again, there's different use cases for this, maybe in R&D. So yeah, to be able to do this is just, it's mind-boggling, really. That I take it for granted now. And yeah, this is one from my colleague Keith. I quite like this. He was offshore and he decided to lock onto a helicopter coming into land, and he got a few frequencies off there just to test the technology. I quite like that one. So we've also used it for bump testing, sort of resonance problems. So because it's transient, we can impact a structure that's offline and actually measure the response of the frequencies. So yeah, we've got some real great uses for this camera. And I'm going to talk later. I've got a lovely case study using this part of the technology where we can actually sync the camera with some a tachometer. So we've put some reflective tape on this pump shaft, motor pump shaft. It's at 3000 RPM and it syncs the camera to that. So we can actually motion amplify a rotating component and actually see the motion and measure it too. So again, really cutting edge developments with this technology. We can also, it's a bit like thermal imaging, I guess, but for vibration, we can overlay sort of color heat maps, but it's for the phase. So looking at how different machines move with different areas. Here we've got a fan on a concrete floor that's got some vibration, and we can actually see how these are, I think this one's 180 degrees out of phase with the floor. So again, really visual ways of looking at these machines now. So just to brief a little bit more on the technology. So it basically measures movement not visible to the human eye, okay? You may have seen on your plant, if you get a pipe that's really vibrating, you can actually see it. Where the camera comes in is where that pipe, then you can't see it move and how it's working on the supports. So it's standard video technology. A lot of these systems use high-grade machine cameras, but a lot of the secret sauce, the magic, I guess, is what they're doing with the data coming out the pixels, okay? So it's all to do with light, okay? And as something vibrates, the light changes. And that's what these systems are able to pick up. So it's measuring the photons of light within that pixel. We can do submicron measurement. And I've seen examples, and I've done some quite higher frequency ones, well over 2,500 hertz. You can go even a lot higher than that, but because the camera's displacement, native unit, displacement drops off with higher frequencies. So I'm not going to go through all these, but it has got so many uses. But I would say in industry, the main ones are rotating equipment, stuff like bases, problems with bases, resonance problems. Piping is fantastic in the oil and gas, especially from a safety point of view. And then structures as well, actual tanks, towers, anything where you might have motion, you'll be able to use this technology to actually visualize and measure. So I'm just going to quickly run through just looking at traditional methods. So we've got vibration analysis, which has been around for many years. Not much change really in this in terms of, it's really the speed of the data collectors, I guess. So we're using a single accelerometer and we're taking readings at different positions, and we're doing that over time, looking for all sorts of machinery problems, from unbalance to bearing defects, and trying to predict before we get a failure. So it's quite low cost per point, but it's very difficult with that to visualize how the machine's moving just with taking a set of readings. To actually imagine that can be quite tricky, and you need quite a lot of experience. Then we've got another technique, ODS, operation deflection shapes, where it's more of a specialized technique where we get data off a machine and we build a model, a 3D model, and we see how that machine moves. And this can give a real insight into a lot of problems on machines. But the downside with it, because it takes so long to do, it's quite high cost per point and time consuming. And generally, historically, this has only been done on probably higher value assets where you might have like a really critical compressor or something. You may have an issue and you're happy to spend quite a lot of money on getting this model down. And then we bring in motion amplification, which is very similar to ODS really. We're basically able to see the operating deflection shape of the machine. We can even do it in live mode now. It's quite crazy. So it's pretty much, you're doing it out in the field. You're not going back to the office to process it. It's there and then. It's quite low cost per point and obviously quite fast to do it. So that's where it sits. I don't know if some of you guys are vibration, but you may have seen this graph. Where the camera sits is the red line. So its native unit is displacement, okay? So it's visualizing displacement, and displacement is more enhanced at the lower frequencies, okay? So this technology is not designed to look for high frequency bearing defects, gear defects, real high frequencies, lubrication problems. It's not designed for that. It's designed to look at the lower end. So if you've got a high running speed vibration, twice running speed, maybe some blade passes, pulsation frequencies we can see with the camera. This is where it's designed for. So traditionally here we can see a picture of a pump, and this is where you'd normally take measurements using a traditional vibration system. What I would say as well, this technology is not to replace by any means traditional vibration. It works really well with it actually. Together they complement each other. So that's traditional vibration, and then we've got MA. So think of every pixel of the camera, and I think there's 2.3 million, which is like putting 2.3 million sensors across that image, okay? And this is what's hard to get your head around when you first start using this technology, because you've literally got so much data. But if there's a little crack, if there's a bolt loose, if something's flexing on that machine, you are going to see it with this technology. And often, quite interestingly, in the background, we'll be say looking at this pump and we see something in the background because the whole image has been amplified. I would say, though, the biggest benefit of the technology is as a communication tool between engineers, because not everyone is a vibration analysis expert or CBM guy. So anyone doing vibration maybe can look at this graph with the peaks, this spectrum, and say, ooh, if that first peak's running speed, that might be looseness. But to a lot of people, it doesn't mean anything. But if I show you a video of that same problem, then suddenly we look at that, it's the Cooper bearing. Oh, there's maybe some looseness there between the D clamp and the cartridge on the inner. It's a lot easier to understand. And this is one of the most powerful things with the technology. And I've had an example with one of my good customers. We've worked there for years. We've found lots of problems. They repaired a lot. And I remember once I found a pump-based problem with my traditional vibration. And I put reports in, and they was a little bit reluctant to do it. They didn't really understand the problem. Did an MA video, boom, oh, we'll get that repaired. So the power of the technology is quite amazing, really. As Paul said, and we've said before, it is a bit of a game changer. It's certainly changed the way I work. It's made my job certainly a lot easier in some respects. And just having to know you've got that technology to be able to visualize that machine vibration, it really, really does help. So where does it sit? It really sits with your routine vibration surveys. If they're picking up problems where you've got raise 1 times and these other frequencies that are not easy to actually diagnose sometimes, it's not always unbalanced. It's not just alignment. A lot of the problems are actually base problems which show up at sort of running speed. It's great for engineering design, root cause, like we've said before, the ODS study. Commissioning, it's really good for, you get a bit of new kit on site, you can scan it with a camera, check not just the machine, the instrumentation that's attached, the pipework, really gives you a good feel for what that machine's doing. So for me, it sits in really nice with your existing PDM teams and condition monitoring setups. A lot of people say, well, how accurate is it compared to normal vibration? Well, here we've got some visual targets and some accelerometers, and there's 2 waveforms overlaid there, and you can't see a difference because there's no difference. They're exactly the same. So provided you've got the distance right, the frequency will always be accurate, but you need the distance to get the correct amplitude. Okay, before we move on to some of the case studies, I just want to show you about frequency filtering. So one of the fantastic tools we've got within this technology, we can actually filter to different frequencies. So when a lot of vibration guys, we take a reading on a machine and we get a frequency spectrum, and within that there might be different frequencies. It might be the running speed vibration, the belt vibration, the pump speed, all these different frequencies. Well, what we can do is filter to an individual frequency. So I'm going to show you here. This is a conveyor. So it's got a motor, gearbox driving a long conveyor. And there's a little, I think it's an oil pump or hydraulic pump attached. So let's play the video. This is the raw data. Okay, there's a lot going on there. There's a lot of movement. This is motion amplified. And you think, oh, where do I start? Well, what we can do, the next video, we have just filtered for the output shaft of the gearbox now. Everything else has been isolated. Okay, it's not in the video anymore. So this is just the vibration, the motion that the output speed of that gearbox is doing. And because it's overhung like this, you do see this time to time on these type of setups. The next one is filtered to 25 hertz. So this, I think it must be the speed of this little motor there. And as you can see, that has definitely got an issue, probably resonance. And it looks like that weld's probably going to break at some point. But what's amazing is we're looking at that now, and we can see that little motor is enough to shake this gearbox that's probably weighs 4 or 5 ton. So your insight into these machines by using filtering, it's really quite amazing. And the last one is a real low frequency. Let's play that, see if you can spot that one. There we go. If you look in the background, there's a conveyor belt there. And that's been excited. I think this is on a raised structure. It's not on ground level, this. So very interesting. One shot, lots of different ways we can view it. So let's look at some rotating equipment problems. So before I play this video, this is probably one of the worst set of bases I've ever seen on a plant. This was a new project, a rush job. And the VA guys said, the VA team said, we're not happy with these pumps. Could you motion amplify it and have a look what's happening? So you can see there, serious base movement, loose bolts, twisting, and I think they were getting bearing defects very quickly on this. Real poor installation. So project team were hauled in, get these pump bases sorted, and here we are now, the before and after. And the right-hand image is motion amplified. And this is the beauty with the technology. It's very difficult to make a good machine look bad with this technology. So that shot there is amplified, but the vibration levels are so low that it's not showing any motion. And that is one of the successes with this technology. So we had a 94% reduction on that one, from 20 millimeters a second down to 1.2. This was on an oil refinery. This was a resonance problem. One of the clues there is it's very directional. If you look at this pump, 25 millimeters per second, and we can see it's not loose. This is the actual excitation. The running speed of the pump coincides with the structural natural frequency. We did a bump test. The natural frequency was 51 hertz. It runs at 49. So we added some stiffening, and you can see that little bracket there underneath the pump, the before and after. And we basically changed the natural frequency, reduced the levels by 86%. And they had lots of problems with that pump, and now it's running happy. This was an early problem we had when I first used the camera, which probably around 4 years ago, actually, maybe a bit longer. So this is on a biofuels plant, this pump, and it wasn't doing horrendous levels. I think it was doing about 3 or 4 millimeters per second, but all the other pumps in this pump alley was 0.5 millimeter per second. So this one had a high 2 times vibration, twice the running speed. And we took a set of readings using the traditional. We could see this 2 times, but we wanted to visualize it with the camera. But before we had the camera, I'd asked these guys, great guys, mechanical guys, check the alignment, check the holding down bolts, and everything they just kept coming back was, we can't find anything. It's good. There's nothing wrong. And I'm like, there's something, because I've got high 2 times. So we put the camera on. Now it is subtle, this is the amplified video. You can probably just see that motor rocking vertically, drive end to non-drive end. If you look at the back end of the motor there, you can see it a little bit more, but it's subtle, it's not horrendous vibration. See the movement there? So what we do with the camera, we look at all the connections. We went underneath at the back of the motor, and that's where we found it. This plate, you can see it's sort of bowed. There's clearance there, that's standard. and then we're going to amplify it. And you can see the subtle motion there, and that was enough to cause the problem. No wonder when they checked the holding down bolts, it felt tight. The alignment was good. So basically, that was the problem. And I think they replaced the bottom and the readings came down. We did a comparison against a machine next door, and you can see that one was good. So yeah, trying to find that without a camera, very difficult. This is one of my favorite MA ones. It's a recent one from a water treatment works. And they had 3 long reach vertical pumps, and one of them suffered quite bad from vibration at different speed, at certain speeds. So again, resonance suspected. So we did lots of tests, and then this is the motion amplified, and it's the pump at the far side. You can actually see the floor. This is on a suspended floor moving. We actually set the machine at the point where the vibration was highest and then filmed it. So you can really see that floor moving. Now, the other pumps actually had supports underneath, but for some reason, I don't know why, they hadn't added them to this area. And the customer knew that, but when they saw the video, it was just so obvious what the problem was. So yeah, classic resonance excitation. When the speed went up, the vibration disappeared. See, it reduces there when the speed's a bit higher. Different speeds we did it at. So I think on this, we did a bump test. So there's me with my big rubber mallet. That's standard footage, but what we can do with the camera, we can actually, this machine's off now, by the way, actually impact there, then filter to the frequency. And you could actually see the floor moving there. Okay. Another interesting one. This was a large pump on a refinery, center hung pump, and the non-drive end bearing, lots of seal and bearing failures. And they weren't sure, they couldn't get down to why this was happening. So again, we got the camera on. It's what we saw with his eye, and then we motion amplified. And we saw very unusual motion. This is solid cast bearing housing, quite large. This is not loose, this is flexing due to the forces within the pump. And what it actually turned out to be, as we always do, we ask a bit of the history. What's the history with this machine? And we tracked it back 2 years previously. It had a failure, and they'd had some machining work done on the housing. And what had happened is that had been incorrectly done, and it almost created like the bearing wasn't sat square in the housing, it was off center, and that was what was causing this motion. And bearings and seals, they just won't last 2 minutes when you've not got everything right. Piping, really good for the camera because it's non-contact and we can look at quite large structures. Here I was on a site, and again we were just asked, could you scan this new bit of plant? I think it was ethanol, this, I think, a little ethanol plant. And if I press play, here we go. So this is motion amplified now. And again, like I say, when there's nothing there, you don't see anything. But right in the middle there, we can see a bit of motion on a pipe. So what we can do, we can get a measurement. I think this was flow induced, just excitation. Change the lens, and we can see there quite a bit of motion on that pipe. And what's great, we can use the Energy Institute guidelines just as a guide for scanning. We can check the vibration level and match those against the guidelines, and it'll give us an indication if we need to do some medial work. And this one definitely was in the concern bracket. You can see there's a lot of strain on that flange there behind. So we can actually look at the frequency, plot the amplitude, and see where it sits. So this one definitely requires some extra support just to reduce that level and stress on the pipework. This is one we had at a biofuels plant as well. It was a steam turbine generator. It was brand new, and they'd got quite a lot of vibration on the pipework. I think they'd had one failure on some small bore tubing. So again, we were asked to look with the camera to see what was happening. So that's what you see with your eye. And then we motion amplify, and we can see it's more than just the little pipe this end. There's a lot of pipework motion. Generally, when you see this movement in the video, it's normally excessive. Basically, we sort of know just by seeing it moving. So we can do some measurements there. We did some plotting against some of the criteria, and again, we was in the concern 20 millimeters per second there. And left alone, this can certainly cause problems down the line. So we then used other technologies. We used this camera and the analyzer, did some bump tests, and found a lot of the pipe work was close, had a natural frequency close to the generator speed. This was a game changer for us using the live MA. My colleague Keith's here. He's got a temporary brace against the generator, and he's tightening it up now, and you can see that vibration dropped as soon as he stiffened that pipe. So this gives you massive confidence on where you want to put brace in, and we can test it out live. That for me is just real game changer stuff. That was before, and then after, with the braces added, you can see the vibration levels are a lot lower. So really, really great to see everything that's happening. Yeah, we was well happy with that one. I think we do some more measurements in a minute. Start that run. Yeah, pipe work, it's yeah, real useful technology. Because again, it's non-contact. To measure that with an accelerometer, you're gonna have to climb over, it's dangerous. And there we go, 0.7 of a millimeter per second now on this pipe work. I think that one was 50 originally, down to 2 there. So real improvement just by adding a few key braces. Okay. Another nice example, this was, I think this is on an FPSO vessel offshore. Again, small bore piping in the oil and gas industry, big problem. We can see here the motion amplified video. You can actually see the stress on where that's probably going to go. So again, this was 25. It's well into the red there. And this one's a case of just adding a brace on there just to change that natural frequency. And we've reduced the vibration levels by 94%. So one of my colleagues, he does a lot of work on these vessels, and I think he goes regularly actually, and does a lot of testing of the whole ship, looking for these problems in commissioning and running. So we saw earlier that we can use MA on rotating components now. This is a recent development really, because you couldn't look at rotating parts. So what we're going to look at here is, this is a plant, a power plant in Rotterdam, and they were getting issues with cracked blades, a lot of cracked blades on these fans. They have a lot. So what we can do is just play the video. Oops. Here we go. So this is the fan running, and then we use the tack sync, and we can actually freeze the motion and look at the blades. So this was the plant. There was lots of these blades here on these fans, and they were getting cracking on the root in a specific area. So we're using a tachometer with reflective tape. We're syncing the camera, so the camera is taking an image every revolution, which then freezes the image. Here's the tachometer. I think it was running at 62 RPM. And that's the shot we get. So this is the old fan design where they're getting lots of problems. And as you can see, when we get closer in, the area where they're getting the cracking, we can see a lot of movement, and then it's very stiff right on the hub. And this, between those 2 points, is where the cracking is occurring. Okay, so it's very obvious with the camera that this was occurring all the time. Now, a lot of the guys on site thought it might be wind related, but I'll come back to that in a second. So what we also did, there was a new fan design that had, and we actually did some shots of that, and we could see that was absolutely fine. The motion was within limits. It was totally different. So comparing the old and new design, we could see there was an issue with the old style blades in this application. The guys on site, like I said, thought initially it was the wind, gusts of wind, intermittently maybe overloading the blades, but we proved it's occurring all the time on every blade. We could even do measurements, which was crazy. We can actually, even though the thing's rotating, we froze it, and we can actually lock on and actually get some displacement measurements. So that is phenomenal bit of technology, quite unique, really. So transient events, because we can just record with the camera over a longer period, we can actually capture all sorts of different types of problem. And what we can also do with the technologies is we can actually use it online with a server. So we had this problem at one of his customer sites. It was in a boiler plant, and it was on the FD fan for the boiler, and intermittently they were getting a noise coming from the fan, and they weren't sure what it was, and it was intermittent. Could you have a look? Could you use your camera? Well, it was intermittent, so we couldn't just sit there all the time. So we basically set up the system, we powered it with a little server, and we actually, this was the cool bit, we used a visual trigger. So we looked at what the fan was doing as it was running normally, and then basically said to the system, if you see over this level, I want you to capture the data. Well, we had it on there a week, and within a week it had nailed it 2 or 3 times. And basically it was the suction side of the fan. There was a lot of motion, and it occurred when we looked at the process data, when the boiler was throttled down. Obviously the airflow was reduced into the fan, and this caused this axial motion on the sucking side of the fan. And what was happening is the casing was actually touching the fan impeller, which was unbelievable. So they're on a project now to isolate this and change the design. So basically when this low flow occurs, that it doesn't transmit the vibration into the fan itself. So it was a great example using the system online. Right, this is another one of my favourites. And what I will say, no one got injured during this one. So we were asked to look at a large gas compressor. And what you're looking at here is actually the lube oil system for it. Behind it to the right, you see a large tank. This is supplying the oil to the large compressor behind. And what they were getting is when they switched over pumps, they were getting a horrendous vibration on this pipework, well over 100 millimeters per second. They were getting failures, and they wanted to visualize what was happening, get some evidence, and I'll play the video. So what you're going to see here is actually what happens when they switch over the pump. So they're switching from an A to a B pump, and you can see these horrendous pipework motion. And right in the middle, there's a bit of a small bore. If you look at that, and yeah, that is not good. I think that was over 200 millimeters per second on that. And sure enough, we actually broke it during this test. You can see that it's failed. Now, the engineer was actually quite chuffed because he said, thank you very much for capturing this failure. I can go back to the big bosses and say, look, this is a serious safety issue. This needs sorting. Again, because it's so visual and powerful, And yeah, it's certainly had the effect in this case. So yeah, the engineer comes in to save the day and turn it off. This is lube oil, this. So like I say, no one got hurt on that one, but yeah, very interesting. This is a recent one I've done. Again, it's just different applications for the camera. Again, this was under strict safety conditions. We had to get permission off the site manager for this. We was well away. So this is a 33 kV HV switch gear, and they wanted to film different operations. They were having failures on the little, I'll be honest, I'm not an expert in this gear. I think the sort of little coils or transformers in the middle, they were getting failures there, and they wanted to see how much motion was there when we switched and that. So I'll just play the video. So on the left is standard, and on the right is the motion amplified footage. I think this is the earth switch in. That was normal speed, motion amplified. Now we can actually slow it down and actually see the contact come down, and we can see the motion there. But beyond that, what they also wanted, again, to show to their OEM, because it was a new plant, this, we actually took measurements off these. These are non-contact, obviously. And we can actually, there's a closer up view, actually. So the white dots are on there is to help with the measurements, because the camera likes a bit of contrast when you do a measurement. So we can see there, we can actually measure the displacement accurately, the movement of those positions. Because what was happening, apparently inside there was some cables and they were rubbing. And when the insulation broke down, these things were exploding. What was interesting is that the arm come down, we can see there how the whole bodies shift to the right for those distances of microns. So you can do some really amazing measurements with the technology when required. So that data's gone to the customer. They'll look at that with the OEM and decide a way forward. Okay. Another tool we can use the camera for is a bit like a strobe, really, I guess. So this is on an oil refinery. Just done some standard MA there. It wasn't particularly bad on the pump itself, but there was a lot of shaft movement on this shaft, not good. So that's running there. We've actually frozen the image, so we can use the technology just like a strobe to visually see. But then what's really cool, we can actually do a measurement on the shaft itself, a bit like a eddy current probe, but with the camera. So we can actually measure the movement there without non-contact. So again, nice little addition there we can do within the technology. Structures, let's have a little look. A couple of structures. So again, this one, it wasn't a major serious issue, but the guys on site said when we're on, this is on a refinery, on the right-hand column at the top, I'm about 250 meters away here. We feel a bit of motion. Do you think the camera could visualize this tower? So we set up the camera, did some measurements. This is what you see with your eye. And there we go. And if you look at the right-hand column, you can see it motion quite a lot, actually. We could do some measurements on that. It's quite amazing, really, that you can actually model such a large structure and be so far away. Again, I'm not an expert on this, but I think they have some sort of dampening towers on their tanks, and this tower didn't have one, apparently. That was why they knew it sort of had motion on there. Okay, this is another great example of the camera being able to use it in non-contact areas. So this is a customer, one of ours, they produce sugar, and this is a sugar beet washing station. So it's like, imagine giant vegetables, a bit like turnips, they're washing them on this shaker screen. Let's play the video. That's what you see with your eye. And then we motion amplify. Now we would expect that screen to move like that, but what we were getting is that there's a drive motor on top there. I don't know if you can just see it. And routine vibration, we got that at 50 millimeters per second. It used to run between 10 and 20. We weren't happy. There was something not right. And when we looked at this video, we could see two vertical supports to the left that were showing a lot of motion. Okay. And again, you get used to seeing this with the camera. We knew this wasn't right. So we looked at different areas of the structure, how it was transmitting. There's some motion vectors showing that side to side, indicating that there's possibly an issue there. This is looking just under the screen. You can see the whole frame is getting moved by this twisting motion. So what we often do with the camera, we'll move position, and here are those arms. And even though it's covered in bits of sugar beet at the bottom, we could tell that we thought these had failed, the actual supports had gone. And sure enough, I think the guys went in, they cleared the beet out, and the supports had sheared off, basically, they'd failed. It does take a lot of hammer, this machine. This is just looking under the frame. So this was before, and then after, they bolted it down and added a support frame as well. This is the shot afterwards. You can see there's a lot less vibration, and it went from 50 down to 12 after they'd done that repair. And I think also they did that on the run. Don't think they shut down for that. So that was pretty good. They didn't have to shut down the feed into the factory. Okay, one more I'd throw in. It might not be relevant for the audience, but maybe. We've actually been doing a lot of test and measurement R&D stuff with the camera, which has been quite interesting for me because it's not a field I'm in. And I just want to show you this nice case here where a circuit board inspection, it basically do like shock tests on stuff like this. So they'll drop it and then they'll test it, see if it still works. And this one failed its shock test, and you can see the motion amplifying it. And we see in the spectrum there, there's the standard shaker table frequencies, but there's some also frequencies there that shouldn't really be there. So what they do is they filter to those frequencies, and then sure enough, we can see there's a capacitor there that's vibrating that I think had an issue indicating it was loose. So what a way, what an amazing use of the technology to find these type of problems, because you cannot put an accelerometer on there. You're just going to change the mass. So yeah, real in-depth use of the technology there. Okay, I think, Paul, that is it. That is not bad timing, actually. That is like 4 seconds to go.
I think that's excellent timing, Stuart. Thank you very much. Great presentation as always. You know, really great examples in there. I have to say, I really love the continuous monitoring solution that you have there. You know, because I've come across these situations before. You know, where you do have at some stage you've got impacting between a fan and the casing, and it's a transient event. You know, and you might be asked to go and look at it, and everything is fine, and you're saying, well, there's nothing wrong with this, and they're saying, well, you don't know what you're doing, obviously. So, you know, but this is great technology, because you know, even though it takes you a week, if you don't do it, you'll never know, and you'll continue getting those failures for the rest of the plant life. So I think it's brilliant. You know, I think it's an amazing thing to have. And I might just add in one little story as well about being a game changer. I think we had a failure of some piping on an AC unit for a server room, so it was quite important, you know. But the AC company had sent in a guy to take vibration readings and all the pipework, you know, and he was actually going to spend the entire day going around with a Jubilee clip and an accelerometer and take a reading and write it down on a piece of paper, and that was his job for the entire day. So we just told him to sit down, and we would take a video in 3 seconds and have his job done, like, you know. So he couldn't believe that it would actually happen, but that's exactly how it is, you know. So I think it's great. I think there's probably more to come. You know,
definitely. I think you just get used to it, though. That's the thing. When I first started using it, it felt a bit alien, and when you've used it quite a bit, you just never say now, or just get the camera out on it, because it's just, I just want to see what's happening. And if I haven't got that tool now, I feel like, I mean, if I'd left it at home or in the office, I'd definitely drive back for it if I was doing a certain.
Yeah, absolutely. I think so. Yeah, even stuff like the small bore instrumentation, or even like, PSVs on Pipework, is there too much motion there? It's a great tool for commissioning and acceptance testing around plants. I have a few questions. One from Arnold Dowling: if you need to add vibration to a chute, can this technology be used to show that the vibration is doing what is required and not causing stresses elsewhere? So I think this is where, sometimes you have a chute at 45 degrees and you want to have a vibration motor just to dislodge any material on the inside.
All right, like a shaker.
Like a shaker, basically. Yeah. And, is this not going to be adding too much vibration elsewhere? I think the answer is yes, you can.
Definitely. I think my colleague Keith's just today actually been to a quarry and looked at that thing, and looking at where the vibration had been transmitted elsewhere, and there was some issue that was causing cracking on some welds. So it's like that screen one I've just shown. You're gonna see motion off the actual vibrating, but then what's it doing elsewhere to the
so it might be doing its job, but is it causing too much vibration somewhere else, which is eventually going to cause a fatigue? That's the big question. Okay, I've got a question from John Byrne: is this mainly used to diagnose the root cause of a suspected known problem on a one-off basis, or would you use it for routine condition monitoring in the same way as vibration monitoring? Or is it best as a follow-up when you identify a problem through vibration monitoring to help find the root cause?
So I'd say it is more of a troubleshoot tool, for sure. And I tend to use the normal walk-around vibration to pick that up. But what I would say is it's definitely used for commissioning. So when you get a new plant on and part of the verification process, a lot of companies now we're working with are writing it into the procedure that it has to have an MA scan and that. You wouldn't really go around, I guess, doing regular routes with it unless you were trying to pick up certain failures that occur regular. So it's more of a troubleshoot tool. But commissioning, yes, it could be used as well.
Okay. No, I'd agree. I've used it, definitely in the pharmaceutical industry and in skids, for acceptance testing, but also where we've had issues. We've had bubble traps that have failed for no apparent reason, but once you put the MA camera on it, it quickly becomes apparent. A question from Gavin McNiff: what frame rate is typically used?
All right, it's a good question. Yeah, so a lot of the problems we're looking at, like we say, is around running speed. So for typical plant, let's say you're looking at the one time, so we'll probably set the camera to something like 120 frames per second, and we'll get an F max of 55 hertz. We can crop the image, or we can use the higher frequency camera. And I think I was doing a job the other day where I had full HD. I was shooting 520 frames a second, and I got a little 530 frames a second, and I got like 265 hertz F max. So it is more for the lower frequencies, but I know with a higher frequency camera, it can actually shoot 28,000 frames a second. But the problem with that is, yes, you'll get an F max of 14,500 hertz, but you're not going to see a lot of displacement at that level, and your image is going to be cropped so much that you're just going to have a few pixels. So it's mainly used, I'd say most of the time, sub 600 hertz is a lot of the work I do, basically.
Right. But I'd say it would be useful for turbines, I guess, the MX camera, if you're going in.
No, definitely. And I know some companies, without mentioning names, a lot of them are using it for component testing, and I've seen some stuff there with turbines where they're looking at components that vibrating at 2,500 hertz to model them and stuff like that. So, yeah, quite special stuff.
Sure. Question from Gavin McNiff: does the software pick the points for the vectors automatically?
No, we can, you put them on manually, so you can put as many as those points on to get your phase and amplitude. Yeah, I think you're unlimited really to do that. Yeah.
Okay, and I've got a question. I didn't see it up on your presentation, but you have done some work for NASA, but you're not allowed to talk about it. Is that correct?
No, not me. I've done a few stuff I can't talk about. It's a bit annoying really, because it's all like the really cool stuff. The actually interesting one, the Formula One car, we just got permission for that because apparently it was a 2 seasons previous car, but until then they wouldn't let us use it.
So. They wouldn't let you use it. Yeah. It's all about the non-disclosure agreements, right?
Yeah, I've signed a few of those.
Yeah. Okay. All right. There's been a few questions about the costs, but we're not going to go into the costs.
Yeah, no.
You know, if you want to contact Stuart, you can definitely reach out to him on his website address, www.rms-reliability.com. Would that be right?
Yeah. Send one directly to me if you want, to Stuart at rms-reliability.com.
Yeah. Okay. Well, I think we're just on time then, Stuart. Excellent presentation as ever. Thank you very much.